Hello everyone, my name is Gongsheng Yuan. I'm a doctoral student in the University of Helsinki. Today I will introduce my recent research, which is storing multimodal data in RDBMS based on reinforcement learning. So let's begin. How to manage multimodal data in a unified way is a significant research topic in the field of databases. To address this problem, we have three solutions. The first one is we could choose different databases to manage different data models in a project, but this may result in operational complexity. The second one is we could use multimodal databases to support multimodal data in a uniform platform with a single unified query language. However, this kind of database is still in the initial state and not as mature as relational databases. Considering relational databases have a powerful ability to handle security, query optimization, transaction management, etc., we think we could try to store and query multimodal data in RDBMS. Due to the mismatch between the complexity of multimodal data structure and the simplicity of flat relational tables, we think it is a challenge to design a good schema for storing multimodal data in an RDBMS. In this research, we attempt to generate a good relational schema based on the reinforcement learning method to store and query multimodal data consisting of relational data, JSON documents, and RDBF data in RDBMS. Why do we use the reinforcement learning method? This is because reinforcement learning is an optimization problem, and we could use the Markov decision process to model the process of relational schema generation. Given an initial state, reinforcement learning could work with a dynamic environment and find the best sequence of actions that will generate the optimal outcome. But it is not easy to employ the reinforcement learning method to learn a relational schema for multimodal data. We need to define its states, actions, rewards, learning algorithm, etc. The figure in the left side is our framework. This framework uses a fully decomposed storage model to preserve multimodal data as the initial schema or initial state. For example, if the number of unique keys in the JSON document is n plus 1, we decompose the JSON document into n two-column tables. Please note that we do not take JSON object ID into account. For the action, we collect and count all the keys, predicates, and attributes in the multimodal data. Next, we map each JSON key to an integer ID from 1 to n. Map each predicate to an integer ID from threshold 1 plus 1 to threshold 1 plus m, and map each attribute to an integer ID from threshold 2 plus 1 to threshold 2 plus p, where n is the total number of keys, m is the number of predicates, p is the number of attributes, and the threshold 1 is a number that is used to distinguish keys from predicates. That means all the IDs of JSON keys are less than threshold 1, and all the predicate IDs are greater than threshold 1 and less than threshold 2. Similarly, we set threshold 2 to distinguish attributes from keys and predicates. Finally, we make each ID represent a join action. This means when the agent chooses an ID, we will use its representative table to do joining. This ID is from a set of actions denoted as A. The benefit of our action definition is to reduce the set of action space into Q, and Q is equal to N plus M plus P. Since we have known all the little table names and the corresponding mapping IDs, we could use them to represent the states, that is, the relational schemas. For example, we could represent initial states as 0 as a string. We use the reserved word 0 as an interval bit between different tables in this expression. We adopt the classic Q-learning algorithm for action selection, whose core idea is to generate a Q table to store state action values. Since we define actions as join operations, we could not make it work just with one Q table and the current state, except that we only do self-joins. This is because we have no idea which table should be chosen from the current schema to do joining with the table corresponding to AI. To address this problem, we have defined another Q table, Qt join. It is Q times Q dimensional table whose rows are defined by a action space. Columns are defined by table IDs, meaning that when first Q table chooses an action AI, the Qt join will decide which table should be chosen to do joining with AI. For reward and goal, we obtain the negative value of query time gotten by the MySQL database performing a set of workload queries on the current relational schema, denoted as minus Tn. When we define the reward as the reduction of this value compared to the previous negative query time, that is TP, subtracts Tn. This is because our goal is to let our agent automatically learn a relational schema having the minimum query time for a set of queries on the given workload by interacting with the MySQL database environment. The above introduction is our main method. As for our experiments, we use the person data set to compare our approach's performance with the multimodal database, RDBMSs. After conducting the data clean, we list its statistics in table 2. As used in table 3, we employ these queries in our experiments, where each query includes 1 or 2 data models. For each QI, we perform the corresponding AQL in RDB databases to get its query time. Besides, we perform all queries 3 times and use the median value in our experiments. Table 4 presents the executing time of queries on the relational schema generated by our method and on RDB. Due to RDB storing data in document format, we can see the query time of RDB is less than our schema when queries only involve JSON, for example, Q1, Q4. For the RDF queries, for example, Q3, our schema sometimes is better than RDB since the triple store require many self-joins. Concerning the multimodal query of Q5, our schema consisting of a mix of binary tables and property tables is better than RDB. And we set epsilon greedy is equal to 0.1 to try its best to explore different schemas. Then we use the optimal schema's query time of each episode to get figure 3 that manifests the trend of total query time as the increase of episodes. Of course, we could set a big number for episode greedy to make its coverage fast. Figure 4 shows the cost of storage space on MySQL and RDB, which denotes the cost of storage space of our schema on MySQL is less than RDB's. So that's all. Thank you very much for your listening, and thank you for the CJ student travel grant to cover my registration fee. And any comments or suggestions?